We humans have long gazed at the birds soaring above, dreaming of joining them in the skies. Our ancestors told tales of winged creatures and crafted kites that danced in the wind. Yet, it wasn't until the dawn of the 20th century that we truly cracked the code of flight. The key? A simple yet ingenious device, the airfoil. An airfoil is the cross-sectional shape of a wing, propeller blade, or even a sail. It's the magic behind flying machines, from mighty jumbo jets to nimble helicopters. The magic, however, is pure physics. Airfoils work by harnessing two fundamental aerodynamic forces, lift and drag. Lift is the force that counteracts gravity, pulling the airfoil upwards. Drag, on the other hand, is the resistance an airfoil encounters as it moves through the air, trying to hold it back. Understanding these two opposing forces is crucial to comprehending the miracle of flight. In the sections that follow, we'll delve deeper into the fascinating world of aerodynamics, unraveling the mysteries of lift and drag, and exploring how these forces shape the way we take to the skies. Fasten your seatbelts. It's going to be an enlightening ride. Lift is what allows heavier-than-air objects to soar. It's the magical force that lets airplanes take off and birds glide effortlessly through the sky. But how does this upward force come about? What are the underlying principles that make lift possible? The answer lies in the ingenious design of the airfoil and a fundamental principle of physics: pressure difference. The shape of the airfoil is meticulously crafted to manipulate airflow. Imagine an airfoil slicing through the air. As it moves, it interacts with the air around it in a very specific way. The air, forced to flow over the curved upper surface of the airfoil, has to travel a longer distance compared to the air flowing underneath. This longer path causes the air to speed up. This difference in distance creates a difference in speed: faster moving air over the top surface and slower moving air underneath. The air flowing over the top moves faster, resulting in lower pressure, while the slower air underneath exerts higher pressure. This pressure difference is crucial. This pressure difference is the engine of lift. It's what pushes the airfoil upwards, counteracting the force of gravity. The higher pressure underneath the airfoil pushes it upwards towards the lower pressure area above. This upward push is what we call lift. The steeper the curve of the airfoil, the greater the pressure difference, and the stronger the lift generated. The design of the airfoil is a delicate balance. Another crucial factor influencing lift is the angle of attack. This is the angle at which the airfoil meets the oncoming airflow. This angle can be adjusted to control the amount of lift. Increasing the angle of attack can enhance lift, but only up to a point. Increasing the angle of attack can enhance lift, but only up to a point. Beyond a critical angle, the smooth airflow over the airfoil becomes disrupted. Beyond a critical angle, the smooth airflow over the airfoil becomes disrupted, leading to a loss of lift known as a stall. This is a dangerous condition for any aircraft. Lift is a fascinating example of how clever engineering can exploit basic principles of physics to achieve remarkable feats. From the Wright brothers' first flight to modern jets, understanding lift has been key. It's the force that allows us to defy gravity and experience the thrill of flight. Whether it's a commercial airliner or a glider, lift is what makes it all possible. While lift is the force that propels us skyward, it is only one part of the equation in the complex world of aerodynamics. Drag is the inevitable resistance we face in our quest for flight. It is the force that opposes the motion of an object through the air, acting as a counterbalance to lift and thrust. Drag is the force that opposes the motion of an object through the air. It is a critical factor that engineers must consider when designing any flying machine, from the smallest drone to the largest commercial airliner. It's the reason airplanes need powerful engines and why a paper airplane eventually flutters to the ground. Without engines to overcome drag, even the most aerodynamically efficient aircraft would be unable to maintain flight. Drag comes in different forms, each with its own unique characteristics. Understanding these forms is essential for optimizing aircraft performance and efficiency. Skin friction drag arises from the friction between the air molecules and the surface of the airfoil. This type of drag is influenced by the texture and cleanliness of the aircraft's surface. The smoother the surface, the lower the skin friction drag. Engineers often use special coatings and materials to minimize this type of drag. Pressure drag, on the other hand, is caused by the difference in air pressure between the front and rear of the airfoil. This pressure difference creates a force that opposes the aircraft's motion. This type of drag is heavily influenced by the shape of the airfoil. A more streamlined shape can significantly reduce pressure drag, allowing the aircraft to move more efficiently through the air. A blunt object creates a large pressure difference, resulting in high pressure drag. This is why aircraft and other vehicles are designed with smooth, tapered shapes to minimize this effect. Induced drag is a consequence of generating lift. As the airfoil produces lift, it also creates swirling vortices of air at the wingtips, which contribute to drag. As the airfoil produces lift, it also creates swirling vortices of air at the wingtips. These vortices create a downwash of air that trails behind the airfoil, inducing drag. These vortices create a downwash of air that trails behind the airfoil, inducing drag. The higher the lift, the stronger the induced drag, making it a significant factor in aircraft performance. The higher the lift, the stronger the induced drag. This relationship means that as an aircraft works harder to generate lift, it also faces increased resistance. Understanding the different types of drag and their causes is crucial for minimizing their impact on flight performance. Engineers use wind tunnels and computer simulations to study and reduce drag. Engineers spend countless hours designing aircraft with streamlined shapes and smooth surfaces to reduce drag and improve fuel efficiency. By mastering the complexities of drag, they help create safer, more efficient, and more environmentally friendly aircraft. While lift and drag are the fundamental forces governing flight, other factors also come into play, influencing the performance of an airfoil. These factors can significantly affect how an aircraft behaves in different conditions. One such factor is air density, which refers to the mass of air molecules in a given volume. Air density can vary based on altitude, temperature, and humidity. Denser air, like that found at lower altitudes, provides more lift and drag for a given airspeed. This is because there are more air molecules to interact with the aircraft's surfaces. Think of it this way. Denser air is like a thicker soup that offers more resistance to the airfoil, resulting in greater lift and drag. Conversely, at higher altitudes where the air is thinner, the aircraft experiences less lift and drag. This is why airplanes need longer runways for takeoff in hot and humid conditions, where the air is less dense. The reduced air density means less lift is generated at a given speed, requiring a longer distance to achieve the necessary lift for takeoff. Velocity is another crucial factor. The speed at which an aircraft travels through the air directly impacts the lift and drag forces acting on it. As the airspeed increases, both lift and drag increase. This relationship is why airplanes need to reach a certain speed before they can take off. The faster the aircraft moves, the more air molecules it encounters, enhancing the lift generated by the wings. This is why airplanes need to reach a certain speed before they can take off. The faster the airfoil moves through the air, the greater the pressure difference created, leading to higher lift. The faster the airfoil moves through the air, the greater the pressure difference created, leading to higher lift. This principle is crucial during takeoff and landing phases where precise speed control is essential. The shape of the airfoil itself is paramount in determining its aerodynamic characteristics. The curvature, thickness, and overall design of the wing play a significant role in how effectively it can generate lift and minimize drag. Engineers spend countless hours designing and testing different airfoil shapes to optimize lift, minimize drag, and achieve specific flight characteristics. This process involves extensive simulations and wind tunnel testing to refine the designs. A slightly different curve here, a subtle change in thickness there. These seemingly small adjustments can dramatically impact an airfoil's performance. The goal is to create a design that balances all the forces acting on the aircraft, ensuring safe and efficient flight.